In this video, I'll be helping you with the ALEKS problem type called finding the inverse of a 2x2 matrix. We have here our matrix A, and we're asked to find the inverse if it exists. So if it exists, we'll give the matrix. If it doesn't exist, we'll say that it's singular, meaning that it doesn't have an inverse. And as we start trying to find the inverse, I'll talk about what might happen that would lead us to choose the option saying that A is singular because it doesn't have an inverse. So to get started, I'll recall that the inverse of a matrix, which is written with the -1, if I multiply A times its inverse, I get the identity matrix, and that goes for either order of multiplication. So if the inverse is put first in the multiplication, I still get the identity matrix, and identity matrices have 1s on the diagonal, and the rest of the values are 0s. So since we're looking at a 2x2, the identity matrix would look like this. If we were looking for a 3x3 identity, it would look like this, and so on. So in this example, we're just dealing with 2x2 matrices. So the process that I will use is to start off with our original matrix here, A, and I'm going to write it with the identity matrix, which is what I want to attain when I find the inverse of A. I'm going to write it in this format. So I've got the matrix A on the left, the identity matrix on the right, and from here I can do some basic row manipulations. So for example, I can multiply a row by a constant. I can also add and subtract rows, and I'll show you what that looks like as we go. But my goal here is going to be through these multiplications and additions and subtractions to turn the matrix on the left, our original matrix, into the identity matrix. And at that point, I will be able to look at the matrix on the right, and that will be A inverse. So looking at this, if I want to turn that matrix on the left into an identity matrix, I need this first element, row 1, column 1, I need that to be a 1. Right now it's a -5, but I can turn it into a 1 by multiplying everything in that row, both the left-hand side and the right-hand side, by -1/5. That would give me a 1 in that first place, and then I can continue to manipulate. But for this first step, what happens when I multiply that first row by the -1/5? Once we distribute this multiplication, the -1/5 times the -5 gives me a 1. And again, that was my goal. I want to get 1s on the diagonal and then the other values to be 0. Multiplying by -1/5 times the -5 gives me that first 1. And then continuing the multiplication, -1/5 times 4 is -4/5. On the other side, -1/5 times 1 is -1/5, and -1/5 times 0 is 0. So for now, I will just bring down that second row. Okay, so we have begun the transformation here. I started making the matrix on the left look like the identity matrix because now I have this 1 in the upper left-hand corner. And I'm going to turn my attention to the bottom row, but keep in mind in the bottom row, I would like for this value to be 0. And not only can I multiply by a constant across the row, I can also add or subtract one row from another. So my plan here for turning this cell into a 0 is that I want to take this first row that has a 1 in the first place, and I want to multiply that by 6. And once I do that, I can take that first row and I can add it, and that 6 that would be in the first place would then cancel with this -6, giving me a 0. So to show what that looks like, this is just an operation I'm doing to the second row. So I'm going to go ahead and bring down the first row. And now I'll start the multiplication and addition. I'm multiplying in the top by 6. So 6 times 1 is 6. And then I'm going to add that to the second column. So 6 times 1 is 6, plus a -6 is 0. Remember, that's my goal, is to get that value to be 0. And then continuing, 6 times -4/5 is -24/5, but then I need to add the 5 that's underneath it. So I'll say plus 5, getting a common denominator would be 25 fifths. So when I add, that would become 1/5. Continuing, I multiply by 6. On the top, that gives me a negative 6/5, and I need to add that to the 0. So negative 6/5 plus 0, negative 6/5, and then once more, 6 times 0 is 0, but then I need to add the value in the bottom, so 0 plus 1 is a 1. So I've completed a couple of steps so far, and I have the 1 that I was looking for in that top left corner, and I have the 0 that I was looking for in the bottom left corner. So to continue to turn this left side into the identity matrix, I want this bottom right side to be a 1, and that I can accomplish by just multiplying the bottom row by 5. Move to the next step here. I'm not changing the top row, so I'll just copy that down. And then in the bottom row, since I'm multiplying by 5, distributing here, 5 times 0 is 0, 5 times 1/5 is 1. And again, this was my whole motivation for multiplying by 5, is I wanted to get a 1 in that position. Continuing the multiplication, 5 times negative 6/5, the 5s would cancel, giving me negative 6, and 5 times 1 is 5. So you can see I've taken one more step towards turning this left-hand side into the identity matrix. I have a 1 in the upper left-hand corner, I have a 0 in the bottom left-hand corner, and I have a 1 in the bottom right-hand corner. Next, I need to turn this value into a 0. And the way that I can do that is to take this bottom row, which now has a 1 in that space, and I can multiply that 1 by a positive 4/5 and then add it to the top row. So my bottom row is going to stay the same, but I'm going to multiply everything in that row by 4/5, and then I'm going to add it to the top row. So 4/5 times 0 is 0. I add that to the top and I get 1. 4/5 times 1 is a positive 4/5. When I add the negative 4/5 in the top, that gives me a 0. Continuing the multiplication, 4/5 times negative 6 is negative 24/5. And then I add the top row, so I'm adding a negative 1/5. That gives me a negative 25/5, or a negative 5 in that space. And then lastly, I multiply 4/5 times 5. That gives me 4. I add the top row, which is 0. 4 plus 0 is 4. So I was able to manipulate everything on the left-hand side, which was that original A matrix, to turn it into this identity matrix. And the resulting right-hand side is now our A inverse. So first of all, somewhere in this process, when I was trying to get these 1s on the diagonal on the left, I could have ran into a problem where I also zeroed out those values. And if I would have unintentionally zeroed out one of those, then that would mean that there is no inverse matrix. I would have chosen the option that said that A is singular. And you may have noticed that for this example, A inverse is actually the same as the original A. The name for that is involutory, but at this point it's just worth pointing out that that doesn't often happen. I would say typically A inverse would be a different matrix than the original A.